Am I audible in the back? Yes, I'm audible. But the slides are not visible. So what were we doing in the last class? What about data? We start with the DRAM cell. The DRAM cell has one transistor and one capacitor. And we said that there is a challenge. You want to see very that? Why do you want to do that? So one thing that we established was whether it is SRAMs or DRAMs. They are all charge storage based levels. They store charge, and when they store charge, that is where they say whether I am storing a 1 or a 0. And in SRAMs, we also see that whatever charge is there, by the virtue of there being a lax there, that charge is replenished. However, in the DRAM, the memory cell is only one transistor and one capacitor. And when that happens, the charge that we have can be after some time, when a lot of leakage has happened, whatever you have stored inside the DRAM may evaporate. I'm using the term evaporate because we are talking about volatile memories. Volatility is something that will vanish, but that will evaporate after some time. So leakage is the cause of evaporation in DRAMs. And what is leakage dependent on? आपके क्वेश्चन भी था area generally so the leakage of this particular one C cell is dependent on the characteristics of the pass gate. If the VT of the pass gate is high, does the leakage be more or less? Less. Why does VT reduce? Why does increase in VT lead to reduction in leakage? Okay. If the VT is high, then it takes a higher voltage on the gate to turn the transistor on. Basically, that current and voltage curve, VGS curve that we had in which we had the logarithmic scale, where we talked about the sub-threshold flow, that entire curve shifts to the right when the VT is high. As it shifts to the right, the current that flows when gate voltage is 0 would reduce, even if the sub-threshold slope remains the same. And therefore, we want to somehow increase the VT of the pass gate. What is the influence of temperature on this? As the temperature increases, sub-threshold increases, right? Because there is more energy for charge carriers to jump into the conduction path and then move from one place to another. So, one thing that is extremely important to realize is that you will be able to play with circuits well only if you also understand the physics behind it. That is why for the EV batch, physics of semiconductor devices are 4 course. That's not a 4 course for EC because EC can go anywhere. But for ET, we have the TSD as a core course. Because the physics needs समझोगे, you cannot really build the circuits around it. So we want this capacitor to be large. What happens when this capacitor is large? What is the advantage of having a large capacitor inside the DRAM cell?
You can store more charge. You can reduce the although you can get the same, but the rate of change or the voltage will reduce.
The leakage remains the same. But now since I have more charge, I don't need to refresh very frequently. So I have more availability of the DRAM. There is shorter periods of time or spaced out periods of time when DRAM is refreshed. That's an advantage to us. But what happens? What is the disadvantage of having a large capacitor? Area. And in every area is we don't want to increase the capacitor size too much. And we look at different kinds of capacitors, how different geometrical structures have been identified so that we can have larger capacitance in the same area. We talked about trench capacitors, fin-based capacitors, MIM capacitors, and so on. And then we looked at the logical organization of the DRAM. We said that the DRAM array is always a square. Why is it always a square? Why do we want it to be square? DRAMs are much bigger than SRAMs. Much bigger. So in the same area, that you wanted to build an SRAM, now you can make 3x, 4x bigger DRAM in terms of capacity. So where an SRAM would have worked with n number of bits, DRAMs, by the virtue of their density, and also DRAMs being the main memory and so on, they are expected to be larger. They need more address bits. And more address bits also means more area. Where does it mean more area?
On the package.
On the package, so on the PCB. So it's not just that you want your device to be smaller. You want your devices also to be smaller. Because if you have smaller devices, then you will be able to pack more onto the same PCB, which reduces the cost of the product that your chips will be integrated on. So we do not want too many things. We want that row address and column address share the same address bus. So if the address bus is 11 bits, I will have possibility to address up to 22 bits in my address space. So if my row address and column address share the same address bus, then the decoding logic will also be similar. And if I have 1, 0, 2, 4 columns, I will also have 1, 0, 2, 4 rows. So my DRAM array is always organized as a square array. The number of rows and columns is the same. Now, when I say square, it is logically square. Physically, there will still be an aspect ratio if it is different than 1. Are you with me? Physically, the aspect ratio may be different than 1, but in terms of number of rows and number of columns, they will always be the same. The logical aspect ratio will be 1:1, but the physical aspect ratio will be different. Or the cell need not be square. Are you getting it? So, ये चीज ध्यान रखना. ऐसा ना हो कि आप ये समझ लो कि हमेशा फिजिकली भी वो स्क्वायर दिखेगा. ऐसा नहीं. And we also talked about this fact that in this square array, we only store 1 bit of every word. So in this big square array, we have only 1 bit of every word. There were 2 raised to power 22 words, 1 bit of every word. this array, square array. So if you want to store 16 bits, you will have 16 such square arrays. In an SRAM, you have all the words of all the bits of a particular word in the same. But that's not the case with the DRAM. In a DRAM, every array only saves one bit. What is the advantage of this? Sorry? Intelligent SRAM method, they are not saying that. What is the advantage of this having just one bit on an array?
Because since now we don't have the multiple bits of the words working together, so if we have some attempts to do with the internet connection, we want to do the entire word, we only do one of the bits of it.
So when you're talking about SRAMs, these data really has an advantage. What is that advantage? The advantage is that in the presence of a high energy particle, if you have a score of larger, then typically high energy particles would corrupt 3 to 4 bits. Now, each of these 4 bits that a high energy particle would have corrupted would come from a different word. So all these 4 words, so even though 4 bits got corrupted, these 4 words came from different, 4 bits came from different words. So every word you just need to correct 1 bit. So a simple error correction code, like single error correction, dual error correction is good enough for you. If you were not to do that at the beginning, then all the 4 words, all the 4 bits will be of the same word. You would have to have huge area of unit for error correction. Now in DRAMs, the cells are smaller. What that means is that the same high energy particles which cost 4 flips in an SRAM can actually cost 16, 20, many more number of flips because the cells are more to be back. So it's a physical phenomenon. And not just a physical phenomenon, also that the DRAMs just store some charge on a capacitor. SRAMs, there are mechanisms to replenish the latch. There's nothing of that sort in the DRAM, so they are much more susceptible to solve errors. But by storing just 1 bit in one array, what we've done is we have assured that even if 10, 20, 30 bits get corrupted, they are just 1 bit of those 10, 20, 30 words. So again, the same kind of error correction which you could have done in SRAMs can be just far more efficient, much more area efficient, power efficient, and overall better. Are you with me? This was where we left. We had started with the fact that because we have this configuration, we would need to have 2 additional signals, RAS and CAS, which would tell which address is being sent on the address bus. What does RAS stand for? Row address. And CAS stands for column address. Okay. So when CAS is asserted, you know that my column address is put on the address bus and I have to access the column there. So let us say one high energy particle hit your DRAM. That high energy particle spoiled 30 bits. But those 30 bits are all belonging to 30 different words. But all those 30 words, only 1 bit had 1 bit. So single error correction, dual error detection code, still work. A separate code that how many of you have read about these error correction codes? Parity checks, sector, and all those things. So, if those of you who have done some courses of communication, you will see that this is a norm there. Because lots of errors get treated because of low SNR. And then you have to apply error correction codes to recover the information. So, as we said, DRAM arrays are logically optimized as square arrays. The number of bits you have, that will be the number of arrays you will have. I'm trying to show them as a 3D thing over here, but they are actually this. We saw the layout last time. Layout thing, the physical organization last time. So they are actually arranged next to each other, but I've just shown them logically arranged like this. Okay. And when the RAS comes, the row address bits select the row, and RAS comes first, and then the CAS comes. Why is RAS required first and decoding it to cutting it?
So that was and then the data line calls the system and then we can pass it on the order.
What's the pipelining it on this one? I send the RAS and then send the CAS. What would happen if I would send the CAS and then send the RAS?
So I have to wait for the whole decoding and then the one decoding would come.
You still have to wait for, when you send RAS first, then you have to wait for row decoding anyways. How can you read without decoding?
If we send CAS, also generally because of the locality of reference, all the bits of words are arranged sequentially. So if we select one word by RAS first, then the whole row is open. And then when we send CAS, so we will extract the first bit, and then we can continue to use CAS to extract the other bits of the same words because of character reference. But we cannot do the same code if we get first because then we have to wait for the whole cycle to complete.
So I could drive when I'm making slide to take me here. But yeah, not to look at things, but yeah. But look at it like this. If we go back to the SRAMs, column address is used to decode bit lines to be connected to the sense amplifier. If you remember this. Now in DRAMs, we last time also saw that as you read, you have to write on every bit line that is selected. So unlike SRAMs, where an SRAM is where the sense amplifier is associated with one set of bit lines, 4 bit lines के साथ या 8 bit lines के साथ या one sense amplifier. In a DRAM, every bit line has a sense amplifier because the refresh has to happen simultaneously. The write has to happen simultaneously. You have to read every bit line, otherwise it's a destructive read. So if you say that you would send the CAS first, what you are saying is, okay, I know which output to select, but the output is not there yet. I'm waiting. Now, RAS comes. I select the row, I trigger the sense amplifiers, then the output comes. And once the output comes, then I have to take some time to set the CAS, the output to the chip there. Challenge here is that CAS cannot be changed until the output has been sent out. So now my entire memory is in the wait mode. What is it waiting on? Output being sent out. However, when I give RA first, what happens? I start to access the memory. I'm not bothered whether the memory access has completed or not. I give the CAS. So my sense amplifier's output also starts to get arranged in the mux. Output is not there yet, but it is already the connections are getting built. Just like we were getting built earlier, they are now getting built. And now, as soon as the array delivers an output, it can be delayed. There's no one waiting. Are you getting it? And then in addition to that, we'll come to that just a little while. What Arpit just said was that I need all the words in a given row. Since I've read all the words, and I know that there is a locality of reference on the cache discussion that we just had responses, I need to carry many words out. Now all the words are available to me near the output. I just need to change the caskets, the column addresses, and I will be able to throw out lots of data to the. I will be able to throw out lots of data to the chip. So it is signal. Not only that, I'm not waiting. Also, I'm enabling burst mode by giving CAS after RAS. Are you able to see this?
There will be one more thing. The sense amplifier decouples the bit line. So it's where you can pipeline it. So the next stage can start the row decoding. Or
So
either
yeah, sense amplifier. Every bit line has a choice. So you don't need to be coupled. It's always coupled. See, we needed to decouple the bit line and the sense amplifier in SRAMs, not just because we wanted to reset, but also because in the next cycle something else will be needed and so on. DRAM में ऐसा कुछ नहीं थी. DRAM में every bit line has their own sense amplifier. No reset required. It's always coupled. Anyways, want to write it to the real memory cell. You want to actually switch the bit lines to 0 and 1. Have to write back. Are you able to see this? In SRAMs, bit lines actually need to decide only just 50 millivolts and your sense amplifier will work. And bit lines can be reset. Because the lab will show the stability of the cell. However, in DRAMs, as soon as you start to read, the charge that was stored in the capacitor vanishes. It is shared with the bit line. That goes to almost VDD by 2. And you have to replenish that charge during the read cycle itself. So, to be able to replenish the charge, you have to read, and the one of the bit line has to go to 1 and the other one has to go to 0. That's a part of the design. So there is, anyways, have to take the bit lines to the desired levels. But nothing about the bit line को charge and disconnect नहीं करना पड़ेगा. Load कम हो जाएगा. You have to do that. That's the design. So every bit line therefore has a sense amplifier. Let's permanently coupled to it. Any more questions?
I was not able to get why DRAM is in waiting state if we send CS.
You send the CS. So your outputs are connected to the outputs of the DRAM. CS have to pass, but the output is not ready.
Once the database
You're waiting. CS is there, but it has nothing to do.
taken care of.
If I send the RAS first,
Have data.
I have the data which needs to be sent forward. As soon as the CAS comes, I can send it across. First motor will just come. So, in DRAMs, there are a few key timings that you need to be careful about. TRAC stands for time from RAS getting triggered to valid data output. It's almost like access time. Okay. TRC is the minimum time from start of one row access to the start of next row access. This is almost like cycle time of SRAMs. Okay. Then TCAS. That is the time it takes from CAS being activated to the output being available. This is kind of the mux delay. And TCAS is actually much shorter because you do not need to go through the RC of the entire array. It's not logical delay. You just need to handle that delay and your output will be there. And now we said that, and this is where the first thing comes in. We said that if I have read the entire row, all the 56 words are available in. I could have started reading from 16th word or 20th word or 50th word, whichever. If I just change the CAS address, I will have the entire new word available to me at the output without having to access the memory array. Are you able to see this? And because TCAS is much shorter than TRAC, it's much shorter than TRAC, what happens is my such access is much faster. This is called as burst mode access, where I will access many adjacent words without accessing the array of the DRAM. And my overall DRAM throughput increases. So TCC is the minimum time from start of one column access to that of the next. And this is much faster than TRAC. Are you getting it? So in random access, you will have to wait for entire TRAC, but in a burst mode access, for the first word, you will need to wait for TRAC, but later you will just need to wait for TCC. So this is how the timing diagrams may look like. And over here, we have brought in the concept of early read and late read. What do you think this is? How many of you have watched this lecture already? Many of you already watched. What do you think this early read is? What is the story about?
The read, the output is enabled before the data will be present in the output. The data can be present as soon as the cell processes the and out of the flash. But in case of the HP, the output enable is enabled at much after the column decoding has happened.
So, DRAMs or main memories are designed to be very, very large. And just one DRAM chip cannot hold that kind of capacity. Because if you try to bring all that DRAM in one chip, then the yield of that die will reduce. Area would increase so much, and yield is inversely proportional to area. You cannot have a very large die. So in every DRAM package that you see, there are multiple dies stacked one over the other or stacked next to each other. All of them accessing the same output bits or same input bits, whichever we get. Now, let us say this door allows only one person to go out, but three of you want to go out. Not possible. But we still want each one of your three to be able to gracefully exit this room. So what will we do? We will say, okay, first you, then you, then you. So that is done by enabling the signal called output enables. Only the die for which output enable is active is allowed to put its data on the output bus. The remaining dies will hold it with them and not put it on the bus. Is that okay? So they have a latch just before the output driver, and that latch holds the data. But the driver acts only when the output enable becomes active. So early read means that my output enable was already active. So as soon as my column address came and my output was ready, it would be asked to leave the room. It would be asked to leave the chip. Be put on the output bus. But suppose your sequence is third, and the first person is presently exiting the room. So you know that okay, मैं यहाँ से चल के वहाँ पहुँच भी गया, so we are waiting. So you're waiting there, and now as soon as your output is enabled, you start to put your output on the output bus. That is late read. Then early read. When we talk of delay, we will talk of CAS throughput delay. But in late read, when we talk of delay, you will talk of OEM throughput delay. There are two different paths, and therefore the delay values are also very different. Is this clear? Any questions about it? Yeah.
There's not exactly this, but in the last that also that we want the state tracking for data to be critical and right that it will
Oh, we're talking about the tax system. Last time we talked about DRAM or domain memory should have or the number of accesses or number of writes that you get should be much lesser than the time of the DRAM, something like that. So you want the DRAM write time to be non-critical, which what it means is that see, DRAM write is going to take responsibility time. You cannot be doing that right at the speed of the processor. Anyways, DRAM में आप कुछ भी processor की speed को तो कर ही नहीं सकते हैं. You should have much slower कर रहे. So what do? Whatever needs to be written, you put it in a small buffer. Now you are hoping that all the write requests to the DRAM will be spaced sufficiently apart so that while I am putting some data in the buffer, by the time the next request will come, the buffer would be empty. I would have written all this data into my DRAM. So how much ever time it takes, I have written a buffer. So my DRAM write is non-critical. If it so happens that I want to write a lot of data into the DRAM, that becomes a challenge. Because then my buffer can overflow. To avoid this overflow, your system will stall. So you don't want to lose data, you don't want to lose information, the system will stall. So you will see everything is kind of now halted and over the system. So there is some overflow that has happened somewhere, which is being handled by the operating system. But it is not that write is very powerful, therefore write is not critical. No, nothing like that. Write is equally slow as read because in read, write also you have to select the word line, you have to read the data. Since amplifier has to now toggle in the other direction so that it can write back the new data into the DRAM, so that all that has to happen. So it is not faster, it is not that it is non-critical like that. It is made non-critical by using a small buffer at the end. Okay. So otherwise you can't wait.
the second definition said that TRC would be greater than TRS because of the extra sense amplifiers and breach or operation. Why the TCC is greater than TCAS? What are the operations something at that point?
Just look at that. So TCAS is आपने स्ट्रोब दिया and output आ जाएगा. But TCC में the new mux has to be selected and the output latch has to be put in a particular state. All those things have to be taken care of, and therefore TCC can be larger. So this is about the write timing. Again, in write also you have early write and late write. Exactly the same concept that your WEN, the data bus, is not available to you as of now. So while your row has gotten selected, everything is ready, the data is not there yet. Only when your WEN will come, then you will be able to pick data from the input bus or the input output bus and then send it inside the array. So early write and early read means that your memory just moves in one flow. Late means that you will have to wait for the signals to be asserted in your favor. This is the same thing that we have to do row access first and then the column access. When you do the column access, the output of the sense amplifier is put onto the data output buffers and that is then sent to the chip there.
main chip there. So अब हम देखते हैं कि what constitutes different kinds of delays. Okay, so row command delay TRCD means that you first have to decode the entire row address, you have to select the word line, and you have to discharge the bit line, read the bit line. Okay, that is TRCD. Take the output to the sense amplifiers. And CAS means I just give the column address, decode it, select the right output of the sense amplifier, and put it onto the output bus. TRAC is a sum of both of them, where you say that column address is now available in advance, and as soon as the output is available at the sense amplifier, it will also be taken across to the output there. This is the delay of precharging the bit line. We just discussed all of this. These are slides that are talking about the same subject. So what happens is in TRCD, when you add the precharge time, that is where you get the delay TRC. Because only after bit lines have been precharged can you give the next step address, the next row address. Are you able to see this?
There will be some more values, for sense amplifier, or is it just the primary of the charge?
Sense amplifier, as soon as you precharge the bit lines, sense amplifier is always coupled with the bit lines.
Also, in the late it is useful when we know the address before that. So before we want to process the data.
Later it is useful when, as I said, you have multiple dies sharing the same output bus, and you get the output enable when you are done. After exit the room, you get output enable later. So this will ensure that large number of dice can be started. Overall capacity can be increased, not looking at the technology that we design. Is that okay until now? Any questions? So, if I use a larger array, which means that I have, like let's say 11 address bits instead of 8. Which of these timings will be switched? Which of these timings will not specify? So I'm asking you, find out certain things will influence switch all timings will change. If I change the size of the array, I change the number of address bits. That means I change the size of the array. Right? तो आपने array का size change करा तो कौन-कौन से डिवाइस change होंगे? तो TRCD change होगा because TCAS should also change. What else? So if TRCD has changed, TRC will also change. What happens to TP? TP remains constant or does it change? The number of ports rather than the recharge time, if you see the same recharge transistor, increase the capacitor delay will increase. Okay. What about practically अगर मैंने array का size change करा, each and every one of these components will change. The percentage with which they change will be different. But each one of them will change. Why will the percentage be different? Why will be the percentage of change be different across these components?
The person RS will be greater than
All these delays are a combination of some RC delay and some public delay. That ratio is different for each one of them. Is it not? So when I increase the array size, do I also change the logic significantly? Somewhere I will need to change the logic, but essentially RC component definitely changes multiple times. R also changes, C also changes. Those square के term में change होने लगता है. So RC component starts to dominate, and whichever of these parts RC was already a dominating component, there the percentage impact will be captured. Where RC was not a dominating component, there the percentage impact will be smaller. Each channel will change, but will change differently. So what happens now? Suppose I have designed for one particular array size, and this question is very relevant to SRAM also, by the way. It's not limited to DRAM. This is about your overall understanding of a memory system. So I've designed an memory. It works fantabulously well for 512 rows and 512 columns. I've changed the array size to 768 rows. And let the column be 512. Okay, I'm talking about an SRAM. So what would change? Like, as a designer, do you think do something more, or is it okay? If I have to faster, they are more lesser. I change the number of rows. Let the columns be same.
decoding time will increase.
Instead of time, the boundary will change. As a designer, what do you need to verify again? Yes. Yeah. I will design. See, आपकी आधा क्विज है, पूरा सिलेबस आ रहा है, और आप इस जैसे क्वेश्चन का नहीं ले पा रहे हो कि आपके डिजाइन में टेक्निकल बेसमेंट अ लॉट ऑफ टाइम इन द क्लास, तो नहीं पता रिकॉर्डेड लेक्चर्स में कितना है नहीं, but class spend a lot of time. So आप अगर ये नहीं बता पा रहे हो, there are so many race conditions that recharge should be turned off before the word line goes on. This should happen before that happens. Each of these race conditions will change because now these days the word line has much longer vertical side to walk and then come horizontally, whereas recharge can just walk horizontally straight away. And the recharge RC has not changed. Word line today has increased, recharge delay has not increased. Something is going to give. Some new marginality, some new race conditions will appear. Or whatever race conditions you already identified, they will move differently and you will have to recharge everything as a designer. See, किसी को पूछते हो, किसी भी लर्निंग को आप इन्फॉर्मेशन की तरह देख सकते हो, तो आपके लिए चैट जीपीटी सफिशिएंट है. But that information will grab करके very quickly. That will not help you. Volatile है, वो आपके इंटरव्यू में volatility से दिखा देगी कि आपको कुछ नहीं आता इंटरव्यू. Or you can understand the subject, internalize it and apply your brain. अच्छा क्या होगा?
Please look at application. I'm insisting that application is far more important than information. Being able to apply what is being taught is far more important. That was what was the entire midsem exam was about. Was it not? It was very simple application of whatever was discussed in the class. And this is what people expect when you do a course, that you are able to apply what has been taught. Just watching video lectures will not teach you that. You'll have to do numericals, you'll have to understand, you'll have to work things out. Okay. So this is again the same story put in a different format. You can watch that in the video. If there are any questions, though for those who've already watched, you can ask. सबकी नजरें वहां चली गई हैं और उसके बैग पे. If you have some X-ray machines, you would also read out what is written on this question paper there. Okay. Yes.
So it might also want to select the address further into two parts. We select as a small lead and into two sides.
So until now, we use only two cycles, one for lower and one for power. But because there are multiple types now, and we'll just look at that. What we also do is we do the reading of outputs. DDR2, DDR4, अभी जो मैं बात कर रहा हूँ ना, अभी क्वेश्चन पेपर में है. मुझे पता था कि आज के बाद क्वेश्चन पेपर में बात होगा. अभी वाली बात भी क्वेश्चन पेपर में है. So all these DDR2 and other output protocols that we have, they are about ensuring that my overall capacity doesn't increase without my die size increase. So we still use only two cycles for DRAM and column address information transfer. Yeah, आगे कोई नहीं बैठा हमारे पास, आगे बैठ सकते. तो we still use only two cycles.
Also, would it be some advantage if people have DRAM based? So, supposing we have DRAM based much closer to the processor, would be implemented much higher bus.
See, even if there is an upchip DRAM, that is, for example, embedded DRAM, you would not want to waste a lot of area and use 256-bit bypassers. Because area is gold, even at the soft level. So you would want to do the multiplexing aspects of the DRAM much faster and then send all the required information to the bus.
So these timings that have been shared, these timings do not include the time it takes to drive an output onto the PCB and then onto the microprocessor. So those delays will be still larger, but these are representative of some time back. Okay. In addition to that, what we also need to see is that in every array, by the virtue of giving RAS and CAS, I will select one bit and one bit only. And when it comes to multiple bits, we're talking about, logically speaking, the depth of that cube. And what we'll see later is that इस cube के नीचे एक छोटा सा buffer लगा दिया जाता है. छोटा सा buffer मतलब इतना छोटा भी नहीं होता. It's like a SRAM that is put there, which stores all the information that comes from the DRAM in the intermediate state, so that whenever the OEM starts to come, my DRAM can start to get data out. Okay. And we already talked about these timings and how a typical system would look like. We already discussed much earlier that these state machines are so complex that there is necessarily these days not just a controller, a separate controller, but also a ampere coprocessor. There's a coprocessor that handles all the interface of the DRAM with it. And
the complexity of the on-chip caches is such that वहाँ पे आपको एक अलग controller लगाना पड़ता है.
So as things are scaling, more things are getting packed. We have a memory controller which does all the interaction with the microprocessor, and the DRAM never actually practically interacts with the microprocessor directly. Now to improve DRAM performance, so ये हमने अभी देखा कि this was the burst mode that we were just talking about.
That you will give one row address, and then you will give a series of column addresses. And this is done because we know that the column address delay is much shorter than row address delay. And as a consequence, my throughput can be much higher. We just discussed that this is called as the burst mode. Yeah. So, those of you who are visiting this class for the first time, or the second time, or the third time, I'm not sure आपको अभी class में कितना समझ में आ रहा है, because I'm not used to seeing your reactions until now. And by the way, the reactions are also not there even today, so I can't make out much. But I would suggest that don't be visitors in your class. You should be residents in your class. I want you to be treated as residents, but you have to behave like residents then. Okay? So you see this N cross M SRAM that I talked about, that in the bottom of the DRAM. Over here, we will put a small SRAM, which stores all the words in the intermediate duration, so that as the column addresses keep coming, my next words of the SRAM are made available. So you were asking कि मेरा next column address मैं कितना जल्दी दे सकता हूँ. That is also limited by the speed of the SRAM over here. Because in a burst mode, now you're not touching the DRAM or CAS part. You're just reading the next word from the SRAM. Are you able to see this? This is actually much faster than what DRAM would have done. So the SRAMs are faster. But this is what defines it, limiting the area. Okay.
So that bits, like they are derived from the DRAM and taken as a group for their successor.
So M bits means that I wanted a 512 cross 64 DRAM. I want to go very simple actually. I wanted 1 megabit DRAM, and each word has 4 bits. Then M is equal to 4. This is the number of bits that we're talking about for the output. So you need a N cross M RAM. Because आपका जो भी आपका कॉलम बिट है, सपोज आपका 512 क्रॉस 512 का एक ब्लॉक है, तो 512 विल बी n, एंड अगर आपका 16 बिट का वर्ड है DRAM का, तो m विल बी 16. Is that okay? It is for one set of words, one line you may say. Okay, so if you would, so one thing is clear, that I have read 256 words or 502 words in one book, and now depending on my line length, and I want to read 16, 32, 256, all of them out. And I do not want to go into the main DRAM again every time I want to read the next word. All this data that I read once has to be stored somewhere. That yes, now you just need to give the address to the SRAM, and the address will be, and the output will be available. Oh, that is just a convention. So my question was, why are all these signals active low?
So this is just a convention that they said that okay, active low रखेंगे तो ऐसा होगा, nothing else. So this is about how do we increase the bandwidth or how do we estimate the bandwidth of a DRAM. So हमने कहा कि हमारी 16 bits की DRAM है. Each block is 1 megabit. Each block is 1 megabit and I have 16 such blocks. So 16 megabit की पूरी DRAM हो गई. And I have 4 such packages, 4 such dies placed next to each other. So overall my DRAM has 64 bits as output. My DRAM chip has 64 bits as output. Is this clear? 1K cross 1K ka array. Every array and 4 such 16 such arrays in one die. So every die has 16 bits of 1 megawords. 4 such dies. 64 megabit ka DRAM ka chip package. I want to find out what is the peak bandwidth of this package. What would it be?
8 bytes, but after the first, like
Peak bandwidth is कभी भी peak हो सकता है ना. तो आपके लिए highest fastest speed कब आता है? जब आप खाली column address change करते हो, फट words start to go up. What is the width of one word? 64 bits, 8 bytes. And what is the TCAS or whatever is given? 40 nanoseconds. So the peak bandwidth is 8 bytes upon 40 nanoseconds, which is equal to 190 megabits per second. And you see, if I have to just read randomly, one word at a time, what is my speed? 8 bytes per second. So from something like just 70, I've gone to 190, 2.5 times, just by using this person. I mean, that's the advantage of fetching the entire line. जब cache की बात कर रहे थे तो set की लाइन ले आएंगे, locality का benefit है. Not just that, overall bit penalty reduces. Because now so many words will actually come just directly. First word will come after 110 nanoseconds, but so many words will come quickly right afterwards. Is this clear?
page mode access lines TCAS.
Yes, because you just need to change the column address and you will get the new word. Okay. So now I wanted 64 bits. There could be multiple ways. I could have. So अभी हमने क्या करा? मैंने 4 डाइस को रखा और उनको पैरेलल में आउटपुट की तरह भेजा. I could have also interleaved. There are a number of pins in the output bus will have reduced. Interleaved means allowing late read and early read and everything so that I can juggle with the same number of pins. And I could have kept it as wide. Typically बहुत wide करने में performance का नुकसान होता है. Performance का नुकसान होता है तो RC vertex हो जाते हैं. And area you lost. Typically, interleaved access is what is that? Because simple access is very slow. Simple access won't work. But wide access is also very difficult. However, Madhav, when you ask that अगर मेरा on-chip DRAM होगा, मेरे पास bandwidth की कमी नहीं है, then one could still think of wide access, but वहाँ पे area का बहुत loss होने लगेगा. So one has to be careful. This is what interleaved access looks like. That while your first memory is pushing something on the output driver, or second memory is pushing something on the output driver, there is some other operation happening on the other dice. As a consequence, my overall throughput is much faster. It's like pipelining. Okay? So by the time you access the final bank, your first bank is also ready for the next access, and so on. So aaj to nahi, but be alert that in your final exam, you will definitely get some questions around DRAM bandwidth and DRAM performance, or probably in the next offline quiz, you will get some questions around DRAM performance and all that. So work on the numericals for those things there. Okay. We'll stop here. There are a few more slides, but they don't have any significantly different data. You should be able to handle them from the online videos directly. We'll stop here and we'll start from the DRAM reference design in the next class. All the best.